Alright, let's start. Okay, and house robber. Oh my gosh, this is 4. House robber 4. Interesting. Alright, so in the rare gift, choose a pile. If there's more than one pile with maximum numbers of gifts, choose any. After k seconds, with the maximum numbers of gifts. If there is more one pile with maximum numbers of gifts, that's the 4 of the square root. Let's say we add 10 and we add the 8 and we add 5. Alright, so each seconds, let's say we just sort it. So we start it, and goal is that find the maximum values it can get, and choose k. So idea is we first convert gift to square and sort, choose top k. So alright, so sort the gift. R begin, Rn. Choose top k. Return the answers. Was finally the last pile, and it's chosen. And it gets 3, so it's 5. Remaining it's 5, 8. Left behind the square root is number takes the race of it. Or I mean, no idea. So actually we're gonna do is 110, and the second part we choose in the 6. We'll get a file. So let's say it's 10. You got 8. You got a remaining, or so left behind the 4 of square root numbers of piles in the I may know that. So let's say with the last pile is chosen, and we'll get behind the 4 of square root numbers. So take erased. Square root. So it's actually alright, so we want to remain it. Actually it's PQ. We use the max heap and alright, so each time we choose it. Alright, so actually it's that we simulated. And we got a 10. Got 3s. Got 8. 1, the 2, the 3. And we will get, if there's a multiplier with maximum, then behind the first square root, it's I say I don't understand it. The last part is chosen again 3 is the why 3 is the because we are choosing the square root. Oh man, I may know the answer. So it's this. That's it. Alright, so I just misunderstand the problem. Now look on the vowel string range. Vowel string to the array queries and find number string representing inclusive starting with the value vowel. Let's say the numbers of string range is that it's given that they are the words start and end with so let's say this is alright, so this is just a prefix sum approach. You know that says course find the numbers of values given a range is start and is alright, so let's define a function. Given the so -1 is lowercase, right? So alright, idea is that you can use the prefix sum to calculate it, and each query you can just do that. This is just we convert to a Boolean function. So let's say in a word, let's say the word ABC and the blah blah blah. Let's say let's convert to the false and the true, and we can do the perfect sum of this. So prefix sum for a word in the words. So if words 0 and this value word back, say the count ++. So you know that the prefix sum list is that the count is it's actually the pre-sum. Alright, so let's say pre will push back the count. We just do query. We can do the O1 queries to do that. So yeah, so it's So if else 0, R minus 1 is the pre-sum of the technology. You can do this 2, 3, 0 and 3, 2, 1. Yeah. About house robbery. Several consecutive streets, so there's a robber steal from robbers first defuse the steal from adjacent holds a capacity of 2. We can steal the old house. What it means is that we only can choose is 2, right? So represent the minimum numbers of house robbers steal for. So that is K house. What it means? We'll steal. Oh, it's always possible to steal at least K house. What it means? A minimum numbers will steal for. Minimum capacity at least K house, or possible way you want to steal. So in order to see that we want to minimize this, we can do that like a rob 0 and 2. We'll get this maximum of 5. Alright. Wait. The maximum amount of this. So we want to minimize the maximum, right? So we want to minimum the maximum steal can get. So steal is the score is that it's maximum skill, maybe I1 blah 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 sort of this, and this should be the number should be greater than K. So what is the idea? In order to see that, let's say here we can see this 2, and you know that it's K, right? So it's what? It's you must can do is either this kind of this, or we can do this kind of this, and it's 2. And yeah, so K is very big. It's more than this, so you want to minimize this. So let's say if we can steal 5, alright, so steal 5 is more than 5, which is this. So let's consider this. Let's say the answer is 5. It's minimum. So in the first example, we'll get this 1, 1, 0. I want to choose is the maximum, the number that greater than K. I want to do this. So compared to the positive integers, we can do the binary search to do that. So this can use the dynamic programming, and if given a 5, we can convert to a Boolean function of this, and we can choose this. Yeah, alright. So we want to maximum the 1, maximum the 1. So if given the answers, let's say the answers, we don't know this, but O is 0, R is 1, let's binary search. Right, so we can use the alright, so if the meat is if this is good, and let's say answer says meat, and we can guess more, smaller, +1, right? So idea. So that's defined about a good binary search, right? So binary search the answers, and each time we calculate the maxima can get. So in order to see the say x, so let's say right, we have the dp function. We don't know this, but yeah, let's say dp functions. And let's say dp0 is equal to if non-zero is greater than I, smaller than x, so return true. Yeah, and so dpi is equal to current value is equal to get. So let's say first is no rob, and if we rob, we can rob, only can rob. So dpi and minus 2 should be greater than k. Let's say good. Right, so say good. Say good is fine too. In order to see that, let's say the 7 and this is 2. Want to minimize then. Oh wait, sorry, it's we get a no rob, and smaller than x is no rob, and rob, and the no rob want to maximum then, and plus 2 minus k. Maximum element get k is good. This is good. Answer is meet. What means? Why does this fail? In order to see this example, let's say what is S and this next element. C is 7 is 2, 5 is 1. What? No rob and rob. Wait a moment. Why this is 5 is dp0 is false, but this guy is true. And we only can rob dp. What the hell is this? I don't understand why. So dp, let's say dp4 is 0 and dp2 is 1 minus 3. 3 is get 1, right? So 3 is get 1 because no rob. It's oh wait. Right. Guys, why are you doing it wrong? It still be here. Still be here. I don't know this, but I am done a very stupid error. Stupid error of this, so I'm not sure, but yeah, it's so stupid. The house robbers just house robbers. So let's say we are doing the inference each, and you're given the basket 1, basket 2, the codes of each basket. We want to make both equal. It means you make both equal. To do that, you can do following operations swap to index swap. Oh, so we swap this 2. We get equal. So 1 is 0, index 1, 2, index 0. Let's say that it's so for 1. Now it's for 1, 2, 2, and basket 2 rearrange them to make them equal. So the minimum codes is swap. The 2 sum here we can. Alright, I know that. So find the min codes to make 2 array equal. Idea is that we don't consider the order, so we can just do equals, no need order. The equal is that it's just this 2 is the same. Whoa. Alright, so I made an idea. Is that it's we can do is that consider me my example the codes we swap them. So first we can do is we have 4, 2, 4, 4, 4, and we have 1, 1, 4, 2. We want to make them balance. So the sum of them must be even. Sum of them must be even. That can be, let's say, negative. Impossible is that sum of each frequency is odd. Right, so it's not impossible. And now let's determine that. How do we commit? So let's just make them equal. Alright, so how to make them equal? And the swap is the cause of this. So I know this, but I need to consider how do we totally find them, because actually it's not just because we need 4 and we need 1, right? So the 1 must be 1, and 4 must be 2, 2 must be 1, and consider that we only can do is swap we can find out each candidate. So let's say because they are greater than 2, so we find out each candidate. Let's say the 4. The candidate size should be the same. And if we want to minimize the codes with a greedy approach, is that it's if we have a 4, what do we do here? We can choose. Say we can sort them. So we have consider we have 2, 4 to move them. And if we have 1 and 2, what is the cause of this? So the 1 must choose the greater, because if we have 5 here, let's say 5, what is the pair? 1, 2. As the pair is the greater, is that it's this pair is going to be 1 and 2. So that just doesn't matter, right? You know, you may have 1 and 2. You may have 1 and 2, but consider that it's there's no need, right? So wait, no need says 0 and because this is smaller, so 0 and 2 is good. It's we can do 1 because we always can separate them. We always can separate them, so we can so let's just get minima. Okay, and find the minima. File minima. Sort. Get to of each candidate. Sort and get half the sum. Half sum is the greater. Let's see. Yeah. So I'm missing this is a good idea, but yeah. So first, do the check on order map. We do a check is count. Basket 1. Basket 2 count. Pause 1 and we first do the check. If these are this is check case 1 of this, and now let's just do the candidate. Can 1, can 2 for X in the basket. If let's just do the basket. They must do the half. They are greater than map. So let's say if map X is, let's say we add map X. So if map X is greater than count X minus n, and can push back the X do the same thing. It's 2. It's 2. And we start. To candidate. If can 1 size is not equal to can 2 size. Alright, we don't start then. Sorry. Let's do this like can insert, let's say original size. We merge them. 2n. So we start them and we just get a half. Get half sum. Merge and sort it. This idea. So that may be the answer actually. can one insert, can one end, continue, that's it. Yeah, I think that's it. It may be the approach. Oh, it's the coach. It's what? It's not be the let's be the 1 y0. Sorry, it's an active one. Can two. Wait a moment. Let's say we have can 2 size is not equal. Let's say y. They are greater minus n. Basically 2 can 2 push 1 and count sizes. Oh, sorry, I forgot to do this. So if this is 1, this b will be by 2 because we only can do is half. So yeah, that's the idea. Oh the greedy cannot. Yeah, the greedy it's not work. So this is greedy. Alright, so greedy cannot work. It's not that simple, right? So candy size must be the same. I know there's a same and it's sort of half sound is greedy. It's not work because this cannot be the best answer of this. So let's consider the value. We want to see why we are fail. Alright, so let's just see ln to see why this is fail. I don't know why this is fail. I currently have no case to determine which is better approach. I'm not sure, but let's see this example to see what happened of this. Alright, so we can get this. Oh, I may know this. So this can be 32 for the choosing then. Oh, what? Oh, I mean no. Oh, wait. We can do this. So say if the 2 is smaller, then 1 plus 1. This can be worked, right? So use the middle, but yeah, we can have another case. It's fail because we can choose a smaller middle to swap length. So in order to see that, let's say we always can choose this guys and this guys and this guys, right? Because we can choosing we can choosing that. It's actually it's like well, whatever, we just move them to this, we can easy to pair them, and yeah, I know we can easy to pair them, but actually I don't know why we are doing bad, because okay, I know this. So this approach is not bad, but I may know the idea is we can use a smaller middle swap. Only can use one smaller middle. We don't need to swap. So we can get this x paired y and y swap z, because we swap to y and let's say y swap to z. So that can move. We can get 2y. So consider if we have 2 smaller in this symbol. So this. Alright, so say have it's not in the candidate, and this is why, because this is already equal, so they are not in the candidate, so not candidate the minimum of this of this is we can we need to choose the common so if I know this, so because this have an 8, right? So this has an 8, so we can use I didn't know this. This one of the mean why this common. What is the common? Common. How do we find a common? This is common. Let's go to one certain foods. So mean. I don't know. Let's say is we can do is so yeah. This yeah, so I think we can use the middle to do that. And yeah, so this can be for 38 because we can use 8 to do this. Yeah, this is yeah, just see. So our edge case is that we can choose middle point to swap length. So we need to care for length. And we always can choose a common to do that. Let's find the common because this is common. So common minimum of this. Yeah. So you have some. Let's either use middle or we just use the minimum because minimum can always dominate it. You always can dominate. We can always rearrange minimum of this. Always. You can always. Yeah. So yeah, so it doesn't matter of that. Yeah, right. That's idea. It's easy? I think it is easy. Alright, so just careful that we can choose because the minimum can use 2 of this edge case, right? So yeah, careful this. That's just the idea. Yeah, but make a stupid error to stupid error. Yeah, so yeah, really stupid. Yeah. Yeah, I don't know, but this is kind of another stupid. Yes, because we can first cases. It's not. It's a H case, you know. It's a H case. With Robland, we have 2 options. It's either current Rob or choose them. But just forgot to do this. Alright, so it's probably true. This make a answer, and this one answer is still be really still be because we can choose 2 middle to do that. Yeah, it's just kind of another stupid problem. This. Hmm. Yeah. So. Where's merge and something? All right. So merge. So right. So it's kind of like a merge sort. Cool. Okay. It's not a hard problem, I think. But just make a stupid error. Yeah, I know this, but just. And the problem one is waste some time to figure out I just doing wrong. Really stupid here. Yeah, but right, just too late. Alright, this matter. I'm done and let's just see the problem. See the problem? Alright, so okay, good. So this kind of problems, I think the 2 and 3 is very similar. But let's see the problem one is not the I just figure out that this is the problem statement. The problem one is that it's you given the pile the gift of this, and you want to every second we have k seconds, and every second we want to choose a pile with the maximum numbers of gift, but we don't calculate them. We don't calculate them, so we just careful that is that when we are choosing them, we are leave the fourth square root of the numbers of given piles. That's the important. This is important. This is the main idea. Is the whole idea of this. So actually, we are choosing a maximum and remain we leave 10 piles. We leave 10 piles of this. Another 10 piles is now 10 gives. So we just use a heap because the k is smaller. So we just try to do is that we keep moving len. And what is a better approach if k is big? We can use Bucky so to do that. We can actually I think we can just not Bucky so we always we also can do is we can use a map to you know it's like a line sweep. But doesn't matter. We can just simulate it, and this kind of complexity is k log n, right? So k log n. All right. So yeah, k log n. It's this will be linear, right? So the kind compress this and space complexity is linear. And what the idea is that we just use max heap and keep choose the maximum and put the square value. That's the idea. So that's problem A, problem one. So and for problem two is very simple because you just try to do is that you want to find what's the number is the vowel Sorry, my English is really bad, but I want to see how to how to how to vowel. Okay, sorry. All right, so vowel. Oh, that's just weird. All right, so this problem is that we want to count a vowel string in range, and it's that given range, and we just calculate the vowel string. What is a vowel string? Is the start and end with a vowel. Yeah. So let's say this is good, this is bad, this is good, this is bad. We can convert to the 0, 1 proper. Convert to 0, 1. Convert to 0, 1, and we can use the prefix sum to fast search the query, because the query may be very big, and if we do linear to check that 0, 1, 2, how many numbers of the vowel string is very slow, so we can use the prefix sum to do that. So let's just use the prefix sum to do that. And if this is vowel, and counter add plus and push back then, and each query we just try to do the prefix sum is left right. I assume that the prefix sum, like because prefix sum is increasing like this. So let's say 1, 2, 3, 4, 7, and 10. This is the prefix sum of this. You want to know the range of the sum. It's actually we can use this sum to minus this sum. You know what I mean. You know what I'm doing. So we can use this. We want to do this. We can use this sum minus all we can get is this sum in range. Yeah. So that's the prefix sum approach. And problem 3, it's another kind of interesting problem, I think. It's that we have the house robbers that we cannot choose the adjacent home, and the capacity is the maximum we can steal. The maximum amount of money you can steal is the capacity, and we want to minimize the capacity. So for example, let's say that we can choose 2. We want to choose we also given the integer k, and want to choose at least k. So in this problem, we're saying that it's we can rob at least 2, but we want to minimize that. So in this example, we can rob 2 and 5. 2, 5. We can get a maximum of this is 5, and this is the minimum, because we can normal way we cannot get 3, because we cannot get 2, because 2 we only have one house, one home, one house, one homes. Yeah, one home. So we cannot do this. So what's the idea? Consider if we fix the minimum of this, it's easy to figure out that. It's easy to figure out. For example, let's say answer is 5. We can easy to figure out it's more than 5. We can mark it as 1, 1, 1. Cover to this. And if we do the maximum, let's say the maximum, DPI is maximum homes we can rob. So consider this. What is the maximum homes we can rob? Ending in I. This is DP, so we know this can be 1, this can be 1, this can be 2. So maximum home we can rob, we can rob is 2, right? So it's actually DP back. That's all we need is DP back. because DP back is maximum can rob. So the idea is that we can either denote the base case, and currently we have two options is given capacity, and we can convert to the Boolean value because this is more than 5, so it's mark as 1. It's more than 5 marks as 1. We can use this. And yeah. So we binary search a value, so we can get the answers, and this is good enough to solve this problem. So yeah, so we can either we'll try to get, and we can know rob. And rob, be careful that the index I, we cannot have this line, so we are adding this line, and this is also for rob. So for rob, we can either rob the okay, we can merge to this to maximum the optimize this. So if we rob len, we are choosing the previous value dp and add a gate if we rob, and we know rob, but we cannot rob this because the maximum is greater, but doesn't matter, we just keep robbing that. So yeah, that's it. Still be good. Alright, so and then we guess the answer. Kind complexity is x, log x, n log x. TC is n log x. Because we binary search, and each binary search we need a linear time. Alright, so that's problem 3. Let's say problem 4. I think it's not hard problem. It's just absurd problem. It's not absurd. It's greedy, and you just figure out some patterns. So you want to you have two baskets, and you want to make them equal. Equals means that we can sort and make them exactly the same. And each time we can do is choose 2 and get a minimums value splits. We can swap them. So in this first example, we can swap 2 and 4. We get this. So we want to know what's the impossible. Impossible is a case is frequencies are odd. So first case is that we determine the frequencies are. This is impossible. So first thing we need to do is track the impossible thing because this is odd. This one, reconnect P1. Oh, wait. Sorry. It's not good. It's not good. It's odd. It's odd. It's odd. Oh, well, this is odd. Yeah, it's odd. Alright, that's not the one, it's odd. What am I doing here? Just waste. Really? Alright, doesn't matter. Yeah, first case is that we check the impossible. And consider that we have and we find out that the candidate means that there's no need. Each array we can find no need. We can no need array no need numbers we want to choose in our land, we can swap them. And observe that we can always choose the first half smallest value. What it means? It means that we have let's say this. We always can choose 0 and 1. We always can choose the minimum. So first you observe that, oh, so the cos is the minimum sum of the top and minimum of two array. This is the first observation. But you are missing a very, very important, you consider this not in the candidate. This not in the candidate, but this is good. This is good. What it means that we can use 0 to swap them. We can move 1 to this. We can move 1 to this. We can move 1 to this because the swap y swap 2 times is no change, you know that. So we can make a swap to 2 step. Make 1 swap to 2 swap. And A swap B, B swap C. So is equal to A swap C, right? So yeah, we just do it, and we only can do is 1 minimum. We never use 2, 3. We never use 3 minimas because no need. This is no need. So we only carries 1 minimus, and you just care that, okay, so common. The common, this is common. Common will be the middle point. So we make the common to find out what is this minimum of this, and get have sum is either get 2 minimum or we can use the smaller one. Yeah, that's the idea. This is a merge part. We merge to candidate to 1, search and choose the top half minimum and care the half. Yeah. This is also important. I think this may be a set because this kind of information, but I think I made a really still be error. Not still be error because this condition make me a set. I know this. Yeah. Alright, doesn't matter. So this following line is doing that. We are calculated if this is greater than the count, we are pushing the candidate. So yeah, it's simple. Alright. This problem 4 hope helpful. Hope easy to understand, and I'm not sure easy to understand, but the code is simple. The idea is simple. Just choose the top minimas because we never use 2. This as a merge sort. You don't want to swap them. The codes we swap them. It's like 1 to maybe 1,000, and we have another 1 and 1 blah blah blah. So that's 2. We can use merge sort. Say the 1 left. We always can swap anyone in the right, so we are erase anything. We erase anything, so we erase anything. And in the 1, another 1, we erase anything, right? So in the 2, erase this. So let's we always can choose the first smaller value, right? So yeah, because we can erase either the left minima or the right minima. It's like the merge, the merge. Just observation. Yeah. That's it. Easy observation. So, alright. So I think I waste a lot of time, but it's not. We don't have China account, so the rank will be the more high. more greater. But China. Oh, I see the China. Oh, yes, China. So, oh, okay. So less than 300. Alright, so it's really? Just two stupid arrow I just make. Oh, okay. Good. This guy. We can do better. Alright, hope I can do better next time. Yeah, so. Alright. Okay, so let's write this.